Understanding half-life can be quite difficult. On the screen in front of you, you see thousands of radioactive nuclei, each one about to give off radiation. However, the exact moment they emit their radiation is impossible to predict. Half-life gives us a way of predicting how long a radioactive substance will stay dangerously radioactive. Where I'm hovering my cursor now, we can see the percentage of atoms which have not yet given off their radiation. At the minute, that's 100%. On the left-hand side, we can see the time that's passed. If I press play on my simulation, I can see on the screen atoms turning blue as they emit their radiation. I am going to try and stop this simulation when half of my atoms have emitted radiation, when I only have 50% left. Okay, so not bad. 49.9% I managed to stop it out. That took 6.5 hours. So the time it has taken for half of these atoms to give off radiation was 6.5 hours. That is a half-life of my sample. If I were to wait another 6.5 hours, I should see that half of what I have remaining will also give off their radiation. So my percentage of atoms remaining should drop to 25%. And the time, in 6.5 hours, should be 13 hours. So I will try and stop this at exactly 25%. Okay, not bad. So 25.2% remaining and 13 hours have passed. I will try again. In another 6.5 hours, I would expect to have half of my 25% remaining. So about 12.5. I will stop my clock when the time has reached 19.5 hours. Okay, and I'm down to about 13%, not quite 12.5, but I think you get the picture. In another 6.5 hours, my 13% will have halved again, and so on. If I were to plot this on a graph, I can see as the nuclei on the left are giving off their radiation, and the activity is plotted on the right, I get a curve. We call this a half-life curve. On the screen, you should be able to see how to calculate the half-life of a radioactive substance from the graph. By looking at the initial starting count rate, the amount of radiation that's given off every second, and then looking for a number which is half of that, in this case our initial count rate is 1, and I'm looking for a half, I can follow a line across to the curve and down to the x-axis, which will be labelled time. The time which appears on the x-axis will be the half-life. This substance has a half-life of 2 hours. The count rate starts at 8,000 counts per second. After 2 hours, the count rate is now at 4,000 counts per second. And after 4 hours, another 2, we've halved again to 2,000 counts per second. And so on. Half-life is extremely important when we are considering the uses of radioactive traces or radioactive substances. Any radioactive substance which we are going to administer to a patient in hospital must have a short half-life. That way it loses its radiation very quickly and the patient is exposed to the dangers of contracting cancer for a much shorter time. Other radioactive elements need a long half-life for their use. For example, carbon-14 is used in carbon dating. The half-life of carbon-14 is 5,700 years.